Hello, Honors Physics. I wanted to give a little bit of guidance on two of the problems from this week's assignment. I got a couple of questions over email from some of you, and so I figured I might as well just make a little improvised video, because probably a lot of people have these questions, so thank you to those of you that wrote to me early about it. Question 6 gives you this diagram and asks about the net force that is felt by the loop, the square or rectangular loop of wire. So we know that wires which carry current in the same direction, such as the straight wire up on top and the top edge, at least, of the square loop, those two currents go in the same direction. And as discussed in the material for this week, currents which flow in the same direction are attractive. So that means that the upper straight wire is attracted to the top edge of the rectangle, and also the top edge of the rectangle is attracted to the upper straight wire. So I'm going to draw a little force vector on there showing that attraction. But if I think about the bottom edge of the rectangular loop, that current goes in the opposite direction from the top wire. So the bottom edge is going to be repelled from that upper straight wire. Now, I've drawn the repelling force as being smaller, and the reason I've done that is because in our formula over on the right about the force between current carrying wires, there's an R there in the basement. So the further apart the wires are, the larger R gets, the smaller the force is going to be. So I know that the repulsive force on the bottom edge is weaker than the attractive force on the top edge. So in order to solve the problem, I would use the formula to calculate both of these two forces. I'll even give them names, F top and F bottom. But you can calculate both of those magnitudes. Whoops. My video paused for some reason, but I think I got it going. So you can use the formula to calculate both of those magnitudes. They have to have opposite signs, obviously, because they point in different directions, but you can get the total force that way. Now you may be wondering why I haven't said anything about the forces on the sides of the loop. The reason is that those two forces are going to cancel each other out. If they didn't, you'd be out of luck, because we don't use calculus in this class, and so there's no way to evaluate it at the honors physics level. But those two forces are going to turn out to be opposites, because everything about them is the same, except for the direction of the current. They're the same distance away from the top wire, they make the same angle with the top wire, they carry the same amount of current. It's just the direction that's different, and so that means the only difference in the forces will be the direction of the forces. So those will cancel each other out, and you don't need to worry about them. Now, let's move on to number 7. This time we are looking at 3 wires that make an equilateral triangle. M is carrying current out of the screen, while N and P are carrying current into the screen. And in part A of this question they ask for the direction of the net force on each wire due to the other wires. So, if I think about the bottom two, N and P, they are carrying current in the same direction, and that means that they are going to be attracted to each other. So what I'm going to do is just sketch in a couple of force vectors. That is the Newton's third law pair of forces, N attracted to P, P attracted to N. If I think about M and N, they carry their currents in opposite directions, and that means they're going to be repelled. So I can draw a vector for M being repelled from N, and a matching vector for N being repelled from M. And then for MP, it's going to be similar. Those currents are also repelled from each other, which is going to give me a pair of forces like that. All of these forces should have the same magnitude because, again, if we look at the formula, the wire, excuse me, the wires are stated to all have the same current I. The triangle is equilateral, so the R is the same in each case. And all of the wires are like infinitely long or something, so they'll have the same L. So I'm going to get the same force magnitude, it's only the directions that are different. So for wire M, if I take those two individual forces and if I were to add them up, I would get a force vector that just goes straight up. Their horizontal parts are going to cancel out. So there's no left or right to the force, but they both point up. So the direction on M is up. For the other two wires, it's not quite as simple, but if you add those vectors together, you're going to have to get something that's basically in between. So you're going to get forces that look something like this. So on wire N, the force goes down and right. For wire P, it goes down and left. So that's it for part A. That's the conceptual part. Part B asks about the magnitudes of these forces, though. And for this, you're going to have to do a little bit of trig. It might give you flashbacks to fall when we were doing free body diagrams and getting components of vectors and stuff. So for M, I'm going to make a new sketch for M. I know I have, that's a bad angle. For M, I know I've got these two force vectors, and the angle between those vectors has to be 60 degrees. Because, again, the problem was stated to be on an equilateral triangle. So there's an equilateral triangle, all the angles in such a triangle are 60, and so this exterior angle also has to be 60 degrees. So there's a few different ways that you could find the net force on that wire. One thing you could do is to think about adding the vectors graphically this way. So those are the two separate forces. And if I add them together, I'm going to get this force. So if I've displaced them like that, that angle's 30. This angle is also 30, which adds up to 60, which means that this other angle is 120. So you could use like law of sines or cosines or something to find the left side there if you wanted to. The other way you can do it is to leave the two individual force vectors where they were, but think about their components. So I know I can split each of them into horizontal parts and vertical parts. The two horizontal parts are going to cancel, since it's all symmetric. So the only part I really need to find is the vertical component. And I have identical vertical components, so I can just find one of them, and then I could double it. And the angles involved here, since I know this is 60, That means that this is 30, and that's 30. And if I were to split the 60 in half, it would become 2 30s. And this diagram is a little nuts. I'm sorry about that. But the point is, you know all of the important numbers for this triangle. And then for the other 2 wires, I'll just do for n. P is going to be symmetric. You could again use either law of sines or cosines if you felt like it, or you can do components. So for example, if I were going to take the components approach, the horizontal force has only an x component. The diagonal force has this negative y component and this negative x component. But I know that this angle here is going to be 30. So once I've calculated the magnitude of the forces, and again, all the force magnitudes are the same, but once I've done that, then I'm going to know the magnitude of these 2 solid vectors in my diagram. That means that I can then get the 2 dashed vectors, the components for the diagonal, add the x components together, the y component of the diagonal vector to 0. That's going to get you the net force vector, which I sketched before, something like that. And the thing to keep in mind, if you're doing the component method for this one, is that since this net force is on a diagonal, you're still going to have to use like the Pythagorean theorem at the end. So let me quickly write out the general idea here. So you've got force 1, x, plus force 2x equals F net x F1y plus F2y equals F net y. In this particular problem, one of those y components is 0, and the other one is non-zero, but both vectors have an x component. And then once you get those net force components, then you do the Pythagorean theorem to get the magnitude. So I would do F net x squared plus F net y squared, square root. That's going to give you the magnitude for the final answer. Alright, so like I said, that was all improvised, so I know it was a little bit disorganized at times, but hopefully it gives you enough guidance to get through it. If you want additional help or discussion of this, just come into my office hours either Thursday or Friday.